Hey there folks, In the last video, I built a hinged apparatus that individuals with refined sensibilities might call a door, and attached it to the front of the frame. Upon completion, it was so magnifique that I dressed it up with Arctic P12 fans that will be instrumental in cooling the system's hard drives that will be added a little later. Next, I assembled some 3D printed parts that assist in bringing power and function to the left side radiator fans, reservoir LEDs, pump tachometer, and front panel LEDs and buttons. With some soldering and some crimping, we were able to connect these devices and test that they all work properly. In this video, I'll be crimping GPU and motherboard cables, assembling the surface mount panel grid on the back of the frame, and more. I'm reminded of Michael Enda's writing in the fantasy classic The Never-Ending Story. What I've started, I must finish. I've gone too far to turn back. I'm not sure how the day will go, but I sure hope that I don't end up killing the build components as a result of miswiring something, and I'd like to avoid sinking into a mire of spirit-draining mud. Let's do this. I've produced a short but quality montage that even Team America would be envious of. First, I measured how long the front fan cables needed to be, removed the fans, shortened the cables to the desired lengths of 5 and 6 inches respectively, reinstalled the fans, and plugged the power cables into the sys_fan7_pump and sys_fan8_pump headers on the motherboard. On the rear left side of the frame, I've added another fan node panel and pre-positioned the cable clasps at these 3 locations. I then made sure that all of the screws in this side's radiator fans match, once again using the M4 30mm zinc-coated steel screws. 3 Silverstone fan filters have been added to the front fans as well. After these beautification steps, I routed the fan cables, zip-tied everything together, and plugged them into the fan hub. Thus concludes the montage. Short and sweet, yet covers the handful of things I took care of behind the scenes. Before I start to add bracket supports for the various cables, there are a couple small tasks I'd like to take care of. The simplest of those is to go ahead and install the power supply. First, I'll loosen the 2 screws on the front of the support arm with a Phillips screwdriver, then sit the power supply on the support tabs, and rotate it up and into position. On top of the frame, I'll thread 4 screws into the power supply's mounting holes, and once all have been started, I'll tighten them down completely. Now I'll apply as much upward pressure as I can on the support arm, making sure to create as much positive contact as possible, and then retighten the 2 screws holding it in place. The second task is a little more involved. There are 4 screws that will be used to secure the power panel to the front of the frame, but the hole in the lower right corner is obstructed by the black corner bracket directly behind it here. Before I start to attach all the brackets, I'm going to finish preparing the area by drilling and tapping M2 threads into that bracket. On the front of the frame, I'll use a pencil to contour the inside edge of the hole so I know where it lines up on the bracket, loosen the 2 screws holding the bracket in place on the back of the frame, and lift it out. Now I'll take the bracket out to the shop, and using a 1/4 inch center punch and hammer, put a pilot divot as close to the center of the mark as I can get it. I want the initial hole to be as straight as possible, so I'm going to use the drill press as opposed to a hand-operated drill. In the drill press, I'll load a 1/16 of an inch drill bit to make the initial hole. With the bracket resting on a couple pieces of scrap wood, I'll put a drop of cutting fluid on top of the pilot divot, flip the drill press on, and slowly drill into the bracket until I reach 3/4 of an inch of depth. After cleaning the shavings off the workpiece, I'll move back to the bench and pull out the mini tabletop vise. To cut the threads, I'll be using a high-speed steel M2 tap with H2 tap tolerance. Rather than using a hand-operated tap wrench, I'll be using my DeWalt drill with the adjustable torque collar set all the way down to 1. This ensures that if the tap encounters even slight resistance, the clutch will slip and prevent the cutting action from destroying the threads or snapping the shaft of the tap itself. I'll secure the bracket in the vise and put a few drops of cutting fluid over the hole. The puddle of fluid will seep down into the opening, which is what I like to see to have confidence that the interior part of the hole is coated adequately. Now I'll gently situate the tap into the pilot hole and apply a consistent amount of pressure on the drill trigger to achieve a slow, methodical spin to the tap. Once it cuts down about 1/2 inch, I'll set the drill to reverse and slowly spin the tap out of the hole. To ensure the threads are good, I'll grab a panhead M2 screw and using a mini screwdriver, thread it down until it's fully seated. Everything looks good, so I'll remove the screw, pop the bracket out of the vise, and head back to the basement to reinstall it. Everything goes back in the way it came out. Put the bracket into place with the tapped hole resting in the lower left corner, and rethread the two M5 8mm screws. From the front of the frame, I can see that the tapped hole perfectly aligns with the power panel mounting hole, and now I can proceed to attaching the GPU and motherboard brackets to the front of the frame. At this point, I can visualize the path that the GPU and motherboard cables will take to reach the necessary ports. The GPU cable will run along the back plate of the water block until it reaches the surface of the motherboard, and will then run along the front of the frame until it reaches the right edge of the motherboard, where it will then make an upward curve and plug into the dedicated 16-pin GPU plug. Following a short initial loop, the motherboard cable will run under the power panel and make an upward curve once it reaches the right edge of the power supply. Depending on the build complexity and hardware components, I've got several styles of brackets I can use for this step. Each one has unique characteristics to satisfy specific use cases. Some are built like a tank but take a lot longer to print. Others are thinner and take up less space, but are also more brittle. For this video card and motherboard combination, I'm going to use 3 distinct bracket designs. The first bracket will route the 16 GPU wires to the right edge of the motherboard. Each of the 6 wire tracks can hold 2 stacked wires with an outer diameter of 2mm, and 1 or 2 28-gauge sideband wires, so I can choose where to place those. The second bracket will route the GPU wires up to the plug on the power supply, and will attach to the power panel. The third bracket will route the 27 motherboard wires to the power supply, with each wire track being perfectly sized to hold 2 stacked wires with an outer diameter of 2mm. All 3 brackets have M2 threaded holes on the front, which are used to secure a small cover plate to hold the wires in position. Mounted using the holes below the 24-pin motherboard connector, the GPU bracket is affixed using M5 8mm screws. I'll loosely thread one screw to hold the bracket in position, and then add the second screw. With both started, I'll make any minor adjustments, and then tighten both screws down completely. To the right of this bracket, the motherboard arm will be installed. I'll use the same process as before. Lightly thread an M5 8mm screw, add another screw on the other side, make any adjustments necessary, and tighten both screws down completely. Now it's time to take this party to the rear. The majority of the remaining area on the back of the frame is occupied by the screws, brackets, and bars that form the skeletal structure of the whole unit, but the area itself doesn't have a consistent depth or strategy for mounting wires. What I'd like to do next is cover this area with a common panel, so as to make it more organized, and have the ability to support a common method of securing cables together. To accomplish that, I've designed a series of simple interlocking panels. Each panel is 4mm thick, and has a grid of surface mount holes that are all tapped with M2.5 threads. The grid of holes is consistent across each panel, with 16.75mm of horizontal space and 27.5mm of vertical space between each hole. Each panel is printed with 5 walls and 100% infill for maximum strength. I like to go in this direction so that the frame is able to remain flexible for all sorts of layouts and configurations. If I need different angles or clasps, I'd rather design a small custom bracket that I can install using the surface mount holes, rather than having to design an entire new panel to support the modifications. The first panel will be installed on the right side of the frame, just above the pass-through box. I'll roll in 4 T-nuts, hold the panel in place, massage the position of the T-nuts behind it, and lightly thread 2 M5 8mm screws on the left 2 holes. Once I get those 2 screws started, I'll massage the position of the right 2 T-nuts, hold a 20mm spacer cube in place, and then insert an M5 30mm screw. Now that all 4 screws are started, I'll get the position just right and finally tighten down all 4 screws completely. The second panel will be added directly above the reservoir unit. First, I'll roll in a T-nut in the center and lightly thread an M5 8mm screw. Then I'll add another T-nut on the right side of the bar, slide the panel to the right, add another T-nut on the left, and then lightly thread 2 more M5 8mm screws. Once it's in the desired position, I'll tighten the screws down completely. The third panel will be added to the top left of the reservoir. This one will take 7 T-nuts at these locations. The 3 mounting holes on the left and right side will be massaged into place and then tightened down using M5 8mm screws. The 7th screw in the upper right corner will have a 20mm spacer cube sat into position and then secured using an M5 30mm screw. The 4th panel will be added directly below the last and will require 6 T-nuts in these locations. Generally speaking, I try and keep about 1/8 of an inch between each panel when mounting, so I'll get this panel into position, thread all 6 screws, massage the alignment, and tighten each down completely. The 5th panel will cover the area behind the power transfer area. For additional support, I'll add a couple small sections of aluminum that measure 3 7/8 inches and 4 1/2 inches long, so I'll go out and cut those now. To attach them to the frame, I'll use a thin type of corner bracket that I've enlarged the holes on using a 7/32 of an inch drill bit, just to give a little bit of additional play as I'm mounting them. Using a ruler and pencil, I'll measure up 4 15/16 of an inch and put a mark. This mark is the reference point where I'll align the top of the first piece of aluminum. Now I'll roll in a T-nut on each side of the inside channels and then massage the 3 7/8 inch length of aluminum into place. An M5 6mm screw will be used on each side to secure the support. With the support ready, I'll roll in 7 more T-nuts, position the 5th panel in its designated area, and one by one tighten the M5 8mm screws down completely. The 6th and final panel will be attached in the upper left corner of the frame. The 4 1/2 inch length of aluminum will be used as a free-hanging vertical support for this panel. Using a ruler and pencil, I'll put a mark at 2 1/8 of an inch from the vertical aluminum support on the left side, roll in a T-nut just to the left of this point, sit the pre-assembled piece of aluminum and corner in place, and tighten the screws down completely. Another 7 T-nuts will be inserted at the mounting hole locations, and then 5 M5 8mm screws will be used for the interior mounting holes. For the leftmost mounting hole, I'll slide in a 20mm spacer cube and insert an M5 30mm screw and loosely thread it on. I'll add another spacer cube on the topmost mounting hole and add another M5 30mm screw. With all the screws started, I'll go back and make any final positioning changes and tighten each screw down completely. And with that, all the panels are installed on the back of the frame. Here you can see how the last panel encompasses the area around the EPS cable hole and the additional hole to accommodate another water tube if such a thing were to be needed in the future. And this panel snugly hugs the rear perimeter of the power transfer area. Now that I've got more paneling than a 1980s mobile home on the rear of this thing, I'll attach the power panel on the front of the frame. The power panel has a series of troughs and ridges that are used to create an apparatus that behaves a lot like a cable comb, without actually clasping around any wires. The depth of each indentation is 4 mm, and the large rectangular area in the lower left corner allows for an 8-pin plug to easily fit through. The track that really ties the room together is 2.5 mm wide, which allows for easy wire mobility between the various compartments. There are 6 surface mount holes that are tapped with M2 threads that will be used to attach the vertical GPU wire attachment, and the power panel itself attaches to the frame with 4 M2 8mm screws. Using my left-hand flipper offer finger, I'll hold the panel in position and add the M2 8mm screw in the lower right corner first. Since this screw position is tapped, adding this one first will hold the panel in position while I insert the other 3 screws one by one. Those 3 screws are also M2 8mm screws, but with no tap threads to put them in, I'll be using these tiny M2 nylon lock nuts on the back of the frame. Since the area is so small, I couldn't film me tightening down the lock nuts, but to accomplish the task I used a pair of needle nose pliers to hold the nuts in place while using a mini screwdriver and Phillips bit to tighten the screws from the front. And with that, the power panel has been aptly attached to the frame. Now that it's in its final resting place, I'll swing back around to the front and add an M5 6mm screw here, and while I'm at it, revisit each of the other screws to make sure they are all tightened down completely. Here's a shot with the last few tasks completed. The last bracket to install is the one that contours the right side of the motherboard and brings the GPU wires up to the power supply. This is a mini version of the larger GPU bracket and has the same specifications as its larger counterpart. Since I know how much you're dying to hear those specs again, they are: The bracket is attached on the left side of the power panel using 2 of the 6 surface mount holes. I've designed this panel with additional holes to allow me to slide the bracket up or down depending on the specifications of the build. But this time I will use the 2nd and 5th positions. Holding the bracket in place, I'll thread 2 M2 6mm screws with the open side of the wire tracks facing the left side of the frame. This bracket also has an M2 threaded hole on the front face, which will be used to secure a cover to hold the wires in place at the end of the process. Alrighty then, all 3 front brackets have been installed along with the power panel, so now we're either going to make some power cables or chew bubblegum. After a short investigation into the large outer pocket of my designer fanny pack, I've discovered that I'm all out of bubblegum, so I guess we'll have to make some cables. Let me spend a few moments describing my process for choosing the wire that will be used in this build. I greatly prefer to use a common wire size throughout a build, since it helps with circuit and connector planning, as well as making it easier to redesign reusable 3D printed parts. The 2 most common wire gauges used in computer cabling are 18 gauge and 16 gauge. However, I have grown quite fond of a less common gauge of wire, 17 gauge in this case, to hook up all of a computer's components. It should be noted that 17 gauge wire is not nearly as plentiful, or available in as many configurations, as the venerable 18 or 16 gauges of wire. Early in a build process, I'll draw up a power delivery plan which includes analyzing the ampacity or wattage requirements for each circuit, and then use this basic spreadsheet template to classify each as inadequate, borderline, adequate, or overkill when connected via 18, 17, or 16 gauge wire. The goal is to pick the wire option with 0 inadequate classifications and the fewest number of overkill entries, while maintaining the constraint of choosing a single wire gauge and using it everywhere in the build, except of course for the fans, LEDs, and front panel connections, whose power can be supplied with significantly smaller, meaning higher gauge, wires. 17 gauge has an upper hand in this exercise though for 2 reasons. The first reason is that I have a ton of the stuff on hand, and the second reason is that with the total diameter of 17 gauge being the same as 18 gauge, except with a larger cross-sectional wire area, there's rarely a reason for me not to pick 17 gauge wire. These classifications are only applicable to my build, components, and opinion. Yours may differ slightly, or they may differ greatly. There are a few products I source for 17 gauge wire. The first is the Alpha Wire EcoWire line. This wire uses modified polyphenylene ether, or MPPE for insulation, has a stranded tin copper core, measures 1.89mm in diameter, and supports up to 600 volts and 105 degrees Celsius operating temperature. One thing I really like about this wire is that with its small total diameter, it makes crimping smaller connector pins a little easier. The insulation is relatively stiff, but is still plenty pliable to use in cramped spaces, the likes of which you might just find in a computer case. Mouser and DigiKey are the first places I go shopping when looking for this wire. The second product I've only recently started sourcing is the mdpc-x 17 gauge hookup wire. It also has a 10 copper conductor core, PVC insulation layer, and supports 80 degrees Celsius operating temperature. One deviation this wire has when compared to the Alpha wire is that its total diameter is 2 mm, as opposed to 1.89 mm, so while that isn't a massive difference, it can be detrimental in crimping circumstances when you absolutely need the smallest diameter wire you can find that will do the job. An offset to that tiny negative against the MDPC's extra size in terms of its diameter would be to buy their Extreme line of wire, which has an even smaller outer diameter than the Alpha wire, coming in at 1.7 mm. That's a sufficient level of detail on the wire I use. At this time, I don't see a need to cover other topics such as max ampacity and chassis versus power transmission settings, ambient temp considerations, derating, or a myriad of other details that could sway a person's decision making when selecting the right wire size for their needs. In summary, when it comes to making EPS, motherboard, GPU, and other types of cables, I've achieved great performance using 17 gauge wire in the vast majority of builds, and will use it again in this one. The first cable I'm going to whip up this evening is the 16-pin 12V high power or 12V 2x6 cable for the RTX 4090 GPU. There are a couple of different connector systems that power the 600+ watt power delivery used on the RTX 4090. One is the Amphenol FCI Minitech Power SEM5 PCIe connector system, and another is the Molex MicroFit Plus SIM5 connector system. Amphenol's specification for power contacts is 9.5 amps per contact, and their specs for the sense, signal, sideband wires, whatever you wish to call them, is 1 amp per contact. These numbers are the spec ratings, not constant utilization values. The SIM5 general product specification for wire size lists 16 gauge for each power termination and 28 gauge for each sideband termination, though it's not hard to find examples where folks, myself included, have been successful using different gauges of wire than those listed in the spec sheet. Since I'm using an early model 4090 that has the original 12V high power board connector, but building a cable using housings marked with the H++ logo, indicating the 12V 2x6 revision, I may also refer to them interchangeably, but I'll do my best not to. On the left is the MicroFit housing from Mod DIY, and on the right is the Amphenol Minitech housing. Both are intended for GPU applications and have 12 power pins and 4 sideband pins. However, depending upon the use case and target power supply, you might have a cable that only utilizes 2 of the 4 sideband wires. Both of these housings are marked with the H++ indicator. When observed horizontally, it's easier to see that the upper body of the MicroFit housing is roughly 1.6 millimeters longer than the Amphenol. There are several variations of power pins that pair with these housings. I enjoy buying pins from different companies just to see what variations I encounter. This pin was purchased from Mainframe Customs. While I was able to make functional cables using these pins, I found them to be the hardest to work with on account of the very small insulation wings. The mating style of the pins I received was the 2-dimple single-seam version. Next up is the Amphenol power pin from Mouser and DigiKey. This is the Minitech high current pin and utilizes one oversized dimple on the end of the pin and is also a single-seam variant. What I like about this pin is the large size of the insulation and conductor crimp wings. I had no problem crimping with 18 and 17 gauge wire, and with a bit more effort got the technique down for crimping onto 16 gauge wire as well. One thing I noticed from both rolls of the pins I received, one from Mouser and one from DigiKey, was that the lock tabs or lock tangs were pressed in too close to the body of the pin. It was very easy to insert these pins into the housing and with almost no effort pull them right back out. However, taking the time to manually flare the tabs out by about 0.5 millimeter significantly increased the strength of the connection. Usually. Next up is the Mod DIY pin, which is a 4-spring single-seam variant. The insulation and conductor wings are the easiest to work with, and I also found the lock tabs to be in just the right position straight off the tape. I had no problem crimping these on 18, 17, or 16 gauge wire. At this time, these are my favorite power pins to crimp with when it comes to making GPU power cables. Finally, here's a comparative shot of all 3 power pins. In the front is the Mod DIY pin, in the middle is the Mainframe Customs pin, and in the back is the Amphenol pin. Moving on to a quick sideband pin comparison. On the left are the pins for use in the MicroFit housing, which I ordered from Mod DIY, and the pin on the right is the Amphenol pin, which is available at Mouser and DigiKey. Both of these pins share a common characteristic. I do not enjoy crimping them. They are exceptionally small compared to other computer-related crimp pins, and I find myself oftentimes needing to work on these behind a helping hands tool just to be able to see what I'm doing. Before jumping into the crimping, let me conclude this section by simply saying that when it comes to ease of construction, performance, and cost, the best combination of housing, power pins, and sideband pins for the 12V high power or 12V 2x6 cables, the offerings from Mod DIY are the best I've used. While the housings aren't likely to be Molex OEM manufactured since they lack the series identifier on the side of the housings, they work great. With all that out of the way, let's crimp some wires. Gathered before me are the hardware and tools I use to crimp GPU wires. 17 gauge MDPC stranded wire for each of the 12 power delivery pins, 28 gauge UL1007 stranded wire for each of the 4 sideband pins, a millimeter ruler for verifying stripped wire length, a pair of micro flush cutters, mini needle nose pliers with smooth, non-serrated inner jaws, a Knipex automatic wire stripper, a Klein Tools curve wire stripper, Mod DIY, MicroFit Plus, 12V 2x6, H++ housing, 4-string power pins and sideband pins, an iCrimp SN58B crimper for the power pins, a PIBA 2030M crimper for the sideband pins, and a Hosen P707 non-ratcheting crimper for additional compression if one of the other two crimpers don't do their job. Although not pictured here, the Engineer Pad series of crimpers is another one I'll use as a backup. With a clear workspace, I'll use the flush cutters to cut sections of 17-gauge wire from the spool. Once cut, I'll use the Knipex strippers to remove 2.5 to 3 millimeters of insulation from the end of the wire. Then I'll use the millimeter ruler to verify the stripped wire length isn't too short or too long. Next, I'll use the flush cutters to remove the individual power pins from the tape reel, and with the wire cut and stripped, and the power pins ready, I'll grab the iCrimp SN58B crimpers and make sure the torque dial is in position 4. For these power pins, I prefer to use the second jaw position in from the outer tip. Despite this position being designated for 20-gauge wire in the documentation, I find that the connection is stronger than the third jaw position, which is the one designated as being for 17-gauge wire. I'll demonstrate more on this in a bit. I'll pick up a power pin and with my fingers, compress the insulation wings just slightly so that they will start to fit in the crimper jaws. Now I'll insert the pin into the crimper and gently squeeze the handles until the ratchet clicks once. After the first click, I'll grip the pin on the opposite side of the crimpers and pull it forward until the insulation wings catch on the transition ridge on the top edge of the crimper's jaw die. Once it catches, the pin will not be able to be pulled any further forward. I will now press the handles again until a second click of the ratcheting mechanism is heard. After the second click, I'll closely inspect the shape of the insulation wings through the jaw opening. If the wings have flared out and formed a crude circular shape, I'll go ahead and insert the wire. If the wings are still mostly straight, I'll continue to squeeze the crimpers until I see the wings rounding out. Now I'll flip the crimpers over to inspect the other side of the pin and validate that the stopper tabs are clear from the crimper jaws. Once the pin is ready in the crimper, I'll take the wire and insert the stripped end into the back side of the crimper opening. With the wire pushed through, I'll rotate the crimpers up so that I can examine the wire as it comes through the crimper opening. What I'm looking for is a 0.5 millimeter to 1 millimeter of exposed wire to be visible beyond the edge of the jaws. If I see the wire extending too far into the pin housing, I'll remove the wire and use the flush cutters to trim off excess wire strands. Or if there isn't enough wire showing, I'll use the Klein curve strippers to remove a little more insulation. To achieve a nice conductor brush flare, I like to see the exposed strands reach 1/3 to halfway between the conductor crimp wings and the back of the stopper tabs. Once everything is in alignment, I'll slowly squeeze the crimper handles until the crimp completes and I can feel the ratchet release, and from precisely that point, release the handles to open the crimper jaws. With some pin and crimper torque combinations, it can be beneficial to squeeze all the way through the ratchet release for a little more pressure. I personally have had better crimps come from these pins by not doing that, but rather stop squeezing as soon as the ratchet mechanism releases. And that completes crimping the first power pin. Let's put all those steps together and do one end-to-end wire crimp example. Now I'll repeat this process 11 more times. Once all the power pins have been crimped, I'll hold the housing with the locking latch pointing up, along with the stopper tabs on the pins facing up, and then push the pins into the housing. Sometimes it's difficult to get a pin to seat fully forward. If that's the case, I'll use a pair of needle nose pliers with smooth inside jaws to gently grip the wire 1 to 2 millimeters away from the housing opening, and then push on the front of the housing while also pulling the wire forward. You have to exercise caution doing this to prevent damage to the insulation or wire. One thing to note is that when I'm making cables using silicone insulated wire, it's almost always necessary to use the needle nose pliers to help insert the pin. since I can't rely on the rigidity of the insulation to help with insertion. And here's how the plug looks with all 12 power pins inserted. I mentioned earlier about my preference for using the 20 gauge jaw as opposed to the 17 gauge jaw on the SN58B crimpers. Let me show you why. Amongst the repertoire of tests I perform on GPU cables is a series of destructive pull tests on wires crimped with 12V 2x6 pins. The tests are administered across samples from different crimpers and torque settings, and in general, are meant to identify the combination of tools and settings that produce the best quality crimps. Best quality indicators include strength of the connection, lack of pin deformation, minimal electrical resistance, etc. To keep this statement concise, I've found that the wires crimped using the 20 gauge jaws were stronger than those crimped with the 17 gauge jaws on account of the added jaw pressure exerted from using the smaller opening. That isn't to say different combinations of die, jaw, and torque settings wouldn't yield crimps that were just as strong, but across my testing, this combination of 20 gauge jaws on torque setting 4 when using the SN58B crimpers has been the best performing combination thus far. Here's a quick example. Right after I was done making the power wires for this cable, I made 8 additional crimped wires, 4 with the 17 gauge die and 4 with 20 gauge die. The wire using the 17 gauge jaw came apart with 12.9 pounds force on average, and the wire using the 20 gauge jaw came apart with 20.1 pounds force on average, demonstrating a 43% difference in strength and above minimum Amphenol testing specs for pull-out force testing. Maybe I'll do a longer video in the future and perform a deeper dive of my techniques and data, but that will have to wait for another day. Hopefully this brief demonstration was at least a tiny bit insightful. With the power pins out of the way, let's move on to the sideband pins. I'm not a fan of crimping these little guys. They're just too hard for me to see. However, with a decent bit of practice, I've come up with a technique that results in successful crimps the vast majority of times. I'll start by cutting 4 lengths of 28 gauge stranded wire from the spool. Then I'll use the Klein 1019 wire strippers to take off about 4 mm of insulation and then straighten the wire out with my fingers. Using the flush cutters again, I'll now cut off all but 2 mm of wire. When working with such small wire, it's easier for me to cut large and trim down than to try and strip such a small amount of insulation to begin with. 2 mm is also longer than the length specified by Amphenol and Molex for their signal pins, but over many crimps, I've found that using a 2 mm length results in stronger crimps and also hasn't caused me any problems. To perform the crimp, I will sit the wire between the insulation wings, 4 to 6 mm ahead of where it needs to ultimately be crimped. Now I'll use a pair of needle nose pliers to pinch the wings just slightly enough to provide a semi-stable grip on the wire. Once there is pressure on the insulation, I'll pull the wire backward until it's resting in the place it needs to be. There should be enough pressure and tension on the insulation to hold the pin in place prior to crimping. Once that's the case, I'll take the PIBA 2030M micro crimpers with the torque dial on the 4th position and using jaw A, which is for 32 to 28 gauge wire, very carefully position the pin into the crimper and fully compress the handles to complete the crimp. As I mentioned earlier in the program, these pins are very hard for me to see, so if I need a little help seeing what's going on, I'll pull out the helping hands tool to make things a little bigger. Here's a close-up of the crimped pin. Once all 4 pins are complete, it's time to insert them into the housing. These pins are inserted with the stopper tabs facing toward the locking latch and pushing them all the way in. Unlike the power pins, the sideband pins do tend to have an audible snap into place once they are fully seated. And just like that, one end of the GPU power cable is complete. I'm not going to spend any time demonstrating how I measure wire length and count on a ruler, so I'll just assume you are taking the steps necessary to figure out just how long your cables need to be. One quick anecdote here. I've never been much for sleeving, as it's just not something that appeals to me. And I can also say that it's cables like these that make me thankful it's not something I'm dedicated to. Because making custom sleeved 12V high power or 12V 2x6 cables is an art form unto itself, and I have mad respect to the folks who are able to consistently produce them with quality. With the first end of the cable completed, and having measured the length of wires for my scenario, it's time to go ahead and crimp the other 12 power pins and 4 sideband pins on the other end of each wire using the same techniques already demonstrated. With those additional crimps completed, I can go ahead and insert the pins into the housing on the other side of the cable. But I have some thoughts on that as well. I've personally used two methods to attach the second connector onto 12V high power and 12V 2x6 cables, but I don't actually know if there is an explicit pinout specification according to the PCI SIG group. On the back of each connector housing, each hole has a designated number. Looking at pinout examples, or using a multimeter, we can see that pins 1 through 6 correspond to energized current delivery, and pins 7 through 12 correspond to the common wire connections. My theory is that it doesn't matter how the pins are ultimately arranged, as long as pins 1 through 6 on one connector are plugged into pins 1 through 6 on the other connector, with the same concept applying to pins 7 through 12. While there is evidence this is true, I have not personally spent the time necessary to further explore the idea. Perhaps I'll do that eventually. The method I use the least is to connect pin 1 on one connector to pin 1 on the other connector, pin 2 to pin 2, and on down the line for each pin on both connectors. I've used this arrangement to power countless GPUs with seemingly no downside. In fact, I'm testing a number of 12V 2x6 cables with 18 gauge wire now that use this technique. The second method I use more frequently is to reverse the pin arrangement while staying in the same row of pins. This results in pin 1 on one connector being attached to pin 6 on the other connector, pin 2 being attached to pin 5, pin 3 being attached to pin 4, etc. This also works just fine. Additionally, one thing that this arrangement supports is attaching cable combs that can slide almost entirely along the cable's power wires from end to end, because there aren't any twists or overlaps along the way. The sideband wires are still a problem for sliding cable combs, but they are fairly pliable and can be beaten into submission. Lastly, I'm not approaching this at all from a cable comb compatibility angle, since I find the combs that you can't take off without disassembling the wires to be an assault on my computering sensibilities. The sideband pins should not be interchanged and must be connected the same on both ends. This means sideband 1 to sideband 1, sideband 2 to 2, etc., so keep that in mind as well. For this build, I am once again going to use the alternating pin method, which is currently represented on the screen. Two final notes on the topic. When I've made exploratory purchases to see what other companies were doing, I found that the cables ordered from Mod DIY are using the alternating pin method, and finally, I've destroyed several OEM GPU cables from NZXT, and they haven't seemed to follow any sort of pattern that I can see. In one cable, for example, pin 5 connected to pin 2, pin 1 connected to pin 1, pin 2 connected to pin 6, etc. With the cable finished, it's ready to be installed in the system. Before I do that, let me show you how I go about removing the pins from one of these connectors if the need arises. On top of that, let me also say that I never reuse 12V high power or 12V 2x6 wires that I've removed from a housing. I consider these pins to be single-use pins. So despite my attempts to cleanly remove them from the housing when necessary, it isn't about salvaging the pins. It's about not damaging the connector housings and reusing them. There are all kinds of pin removal tools out there, some of which are OEM quality, and others that are less so. I keep on hand a ton of these cheap pin removal tools, as well as a specially made option from ModMyMods for 12V high power pin removal. For the power pins, I'll grip the wire, not the connector, push the tool carefully between the connector body and one edge of the pin, and rotate the tool back and forth a few times like so. Then I'll remove the tool, insert it on the other side of the pin, twist a few times, remove the tool, and now try and pull the pin out of the housing. If it doesn't come free the first time, I'll repeat these steps until it does. To remove the sideband pins, we'll need to depress the angled locking tab here. Looking at the connector housing with a wire inserted, you can see that when I pull back and forth, the tab prevents the pin from sliding backward and thus not being able to be removed. I'll pull out the helping hands so that I can see what I'm doing, and using a tool with a tiny tip, depress the locking tab on the front of the pin and then pull it out of the slot. Easy breezy. Now I'm ready to install the cable into the brackets that were added in earlier steps. Since this area is fairly cramped, I'm going to show you the before and after and explain a couple of things, rather than demonstrate the process end to end. First, I'll plug the cable we just made into the GPU power angle adapter, making very sure that the connectors are solidly mated together. Once amalgamated, I'll insert the other side of the angle adapter into the GPU power plug, and make extra sure that it's fully seated by examining the seam between the GPU plug and the top edge of the connector housing. With the GPU connector plugged in, I'll insert the other end of the cable into the power supply, and now start to insert the individual wires into both of the GPU cable brackets, with 2 power wires going into each track, and 1 sideband wire going into each of the 2nd, 3rd, 4th, and 5th tracks in the bracket. Generally, I will start at the power supply and work backward toward the GPU. Once all the wires are in place, I'll throw a couple of zip ties near the GPU, and now this cable is routed all the way back to the power supply. The reason I take the easy route here with zip ties is because I like to cut my cables with roughly 10mm of extra length on each wire, so that if I need a slightly different cable length to support a new graphics card, I don't necessarily have to make a brand new cable every time. With the extra length, cable combs don't really result in a nicer looking end product. I've also went ahead and installed the cover plates on both of the brackets using M2 6mm panhead screws. On the right side of the motherboard, where the cable makes the first upward swing, there is roughly a 50mm bend radius on the wires. There are wire bend radius specifications from the NEC, IEC, and IEE standards, but these deal with wire and use cases that are significantly greater in terms of overall power delivery than the kind of small wire applications in computers. When it comes to situations where bend radius is a little more important, my personal standard when using 2mm 17-gauge wire is to allow for a 6 times bend radius at an absolute minimum, especially when transitioning from one area to another within a case that requires right angle or near right angle bends. Lastly, if I really wanted the area behind the GPU to be Uncle Granny's leek sauce, I'd use this angled bracket and size the wires precisely for a nice effect. The negative to using this bracket though, and the reason I didn't use it here, is that once made, the GPU cable would be sized exactly to this video card and water block, and likely would not fit any other combination of hardware. Between the second bracket and the power supply is another upward angle, where the max angle is roughly 45 degrees, however the range of the bend is across a fairly long distance. My primary goal with this arrangement is to ensure that the point at which the wires enter the connector housing, the wires have had an opportunity to run almost completely straight for at least an inch, rather than being bent and mangled to fit tightly into the space. The smaller sideband wires rarely hang nicely in unison with the larger power wires. Since these are sticking out and messing up the feng shui, I'm going to attach a small custom cable comb that is constructed using a front access M2 6mm screw to assemble the pieces together. With the cable comb in place, things are looking just swell, and I think it's time to move on to the next step, which will be a quickie. To connect the GPU's RGB cable, I'll slide the connector up behind the GPU power cable and thread the cable slack all the way through. You can see here that I've designed the first GPU bracket cover to have an L-shaped angle on the top of the cover. This slight angle will be used to grip the RGB cable as it's routed to its destination. I'll gently push the cable under the lip of the bracket, use a small piece of 3D printed scrap material to push it into place, and then plug the connector into the D_LED2 5V 3-pin RGB header on the motherboard. Now I'll use small 4-inch zip ties to wrangle the rest of the cable into place just under the edge of the motherboard. That wraps up installing the GPU cable. Time to move on and construct the 24-pin motherboard cable. Once again, I'll be using 17-gauge wire, and while there are a few variations of pins available for this purpose, I categorize them into what I consider to be the 2 dominant styles: long wing and short wing pins. These pins are commonly referred to as ATX, PCI, EPS female pins. To sum it up succinctly, from my testing, the long wing variants perform better in destructive pull force tests, are easier to work with, and support any gauge of wire I would possibly ever use to construct a motherboard power cable. That isn't to say that the short wing variants aren't useful, they certainly can be, but for the majority of scenarios, the long wing variants are the ones I use most often. When it comes to constructing motherboard cables, my go-to equipment is as follows: 17-gauge wire, a 24-pin motherboard ATX connector, an 18-pin power supply connector, a 10-pin power supply connector, long wing female ATX PCIe EPS pins, the trade name for these pins is the Molex MiniFit Junior series, Knipex automatic wire strippers, and a pair of iCrimp SN28B crimpers. While I prefer the 28Bs for this pin, the 58Bs, Hosen P707, and Engineer Pad series work just fine here as well, so use what feels comfortable to you. The additional tools and hardware I use for making single to double pin wires is a heat gun, a razor blade or other sharp tool, Klein curve wire strippers, the Hosen P707 crimper, 3/32 of an inch double wall adhesive lined heat shrink tubing, and U-shaped crimp terminals. Most motherboard cables have two distinct types of wires, single pin to single pin wires, and a handful of single pin to double pin wires. Let's tackle the easy wires first, the single pin to single pin wires. The crimping process I use for motherboard cable pins is nearly identical to the process I demonstrated for the GPU cable. Rather than go into detail again, I'm simply going to show an end-to-end crimp with textual highlights. Crimping these single-pin motherboard wires is a straightforward task and isn't difficult with a little bit of practice. With one wire down, I need 18 more, so I'll go ahead and make those now. Once complete, I've got 19 single-pin to single-pin wires ready to insert into the 24-pin connector. But first, let's also craft the single-pin to double-pin wires. I'm using the NZXT C1200 power supply, which needs 4 single-pin to double-pin wires for the motherboard cable, or an equivalent method to achieve that outcome. The first way I'm going to demonstrate making these wires isn't the only way to construct a working 24-pin cable. You could also use small jumper or bridge wires to reduce the number of full-length wires, incorporate specialized hardware to reduce the number of wires if using supported hardware, and also use multiple wire gauges from a single pin. Any of these approaches can be valid. However, as I stated earlier, I prefer for all of the power wires in a computer to be the same as often as possible. So I'll be making 4 single 17 gauge to double 17 gauge wires. First, I'm going to cut 4 lengths of wire that are 24 inches long and 4 lengths of wire that are 19 inches long. On the 24-inch lengths, I'll measure in 5 inches from an end and put a mark with a pencil. Using the other side of the ruler, I'll now make another mark that is 5 millimeters further down the cable from the first mark. With those marks in place, I'll now use the Klein wire strippers to pinch the insulation at those 2 marks. Since this pair doesn't have a 17 gauge diameter to use, I'll be using the 16 gauge hole, but not squeeze the handles all the way down. Now that both marks have had the insulation indented, I'll lay the section of wire flat on the table surface and using a razor, cut the insulation between the 2 indentions. Once there is a sufficient chunk of the insulation taken off, I can use my fingernails and flush cutters to remove all of the insulation between the marked area. On the shorter 19-inch section of wire, I'll strip off 6 millimeters of insulation from one end. To join these sections of wire together, I'll be using half of a U-shaped copper crimp terminal. There wouldn't be anything wrong with using the whole terminal, but to double the amount of wires I can do, and to keep the rigid section of the final wire as small as possible, I prefer to cut these in half. I'll use the flush cutters to cut one side of the crimp terminal, cut the other side of the crimp terminal, and then cut down the center. After the main cut is made, I'll inspect the cut line and make sure there aren't any overly sharp edges or burrs left behind. If there are, I'll clean those up now. For these crimps, I prefer to use a non-ratcheting crimper, as the pressure and angle are much easier to manage than with a ratcheting crimper. Today, I'll be using the Hosen P707. This type of crimper usually has 2 different sections outlined on the jaws, one for conductor crimping and one for insulation crimping. For this task, I'll be using the 3.5 die in the insulation section and the 2.9 die in the conductor section. I'll pinch the wires together while holding the crimp terminal in place and then work the terminal to the 2.9 area in the conductor section. When it's in place, I'll gently squeeze the handles until the conductors are crimped together. This will typically cause the side with 2 wires to flare up a bit, so I'll bend them both back into alignment. Now I'll position the insulation crimp in the 3.5 die and gently compress the larger wings. With the crimp complete, I've now got a single lead wire splitting out to 2 wires. As I mentioned earlier, there's no reason why a full crimp terminal couldn't be used, as you can see in this example, but it creates a much larger area on the resulting wire that will not be bendable or shapeable. And for this kind of cable, the extra crimp length is largely unnecessary. With the wire complete, I'll now cut a section of double wall adhesive lined heat shrink that measures 15 millimeters long. The diameter of this heat shrink is 3/32 of an inch. I like for the heat shrink to be as centered on the connection as possible, so I'll use the millimeter ruler to put a mark 4 millimeters out from the edge of the crimped terminal metal. Then I'll slide the heat shrink to the mark on the wire, and then use a heat gun to melt the heat shrink as evenly as possible. Now that the wire splitting is complete, I'll use a long wing female ATX pin on all 3 ends of each wire. After the first cable is done, I'll repeat these same steps to make 3 more cables. Once the pins are on, it will be time to insert them into the 3 different motherboard power connectors. One thing I'll briefly mention here is that I do not typically solder these connections after crimping. I know that there are lots of people out there that do, and are fine telling you that these connections should be soldered. But unless there is a specific need or variable that requires it and, this is key, you possess a good soldering technique, soldering already well-crimped wires can introduce more problems than it solves. This topic on its own could run a full video, so I'll refrain from delving further into it here. Let me also quickly show you a few other options I've used in the past to make these single to double wires. I've also provided the recognized name of each technique to make them more globally identifiable. The first technique is commonly called the JeBron Lame School of Medicine. This crimp is made by stripping both wires to about 9 millimeters, cut and apply a piece of dual wall adhesive lined heat shrink to all but about 3 millimeters of wire, and then crimp as usual. The next technique is called the 17-minute, one-breath underwater Pasodoble dance competition. Strip one wire to 3 millimeters, strip a second wire to about 6 millimeters, crimp as usual, and optionally apply a piece of heat shrink. The third technique is called the Foldout Comode Usurper. Strip both wires to about 6 millimeters, crimp as usual. This crimp results in no insulation being gripped in the pin wings. I've received several cables from different companies over the years that use this method in their motherboard cables. Here's an example of one I received from Mod DIY sometime within the last 8 months that utilizes this method. And finally, the last technique is called the new Phonebooks are here. The new Phonebooks are here. Strip 3 millimeters of insulation off 2 wires, cut about 3 millimeters of the remaining insulation at an angle with a razor blade or other sharp object, hold the wires with the angle cut facing each other, and then crimp as usual. Part of the reason more exotic techniques like these can work is because the majority of crimp strength comes from the effective connection of the conductor wings to the wire conductor strands. By contrast, the insulation wings provide a bit of strain relief for the overall assembly. At the end of the day, if a cable functions, doesn't melt, and doesn't kill the component it's powering, then it's doing its job no matter how it's put together. However, these are not my preferred methods. With all of the wires made, it's time to put them in their place. The green marks indicate which holes receive the single-to-single wires, and the red holes are those that receive the single-to-double wires. Also for reference, here's the complete pinout assignment between the 3 connectors. With the lock tab on each pin pointing toward the latch on the connector, I'll push each one into the designated hole. These pins do typically emit an audible click once fully inserted. After all the pins have been inserted into the 24-pin connector, I'll plug it into the motherboard, followed by twisting and stacking the individual wires in the cable bracket. Since the motherboard cable has a defined pinout pattern, and that pattern needs to translate on the power supply side in a specific order, the stacking pattern I use for this specific power supply is represented here. By stacking the wires in this arrangement, as the cable makes its way to the power supply, the wires will be arranged in the back to front pin order of the 10-pin and 18-pin connectors. I'm now going to cut a piece of reusable Velcro cable tie that is 2 3/4 inches in length and wrap it around the wires instead of using zip ties. In terms of placement, I prefer to put this directly under the RGB header. Finally, I'll use 2 M2 6mm screws to attach the cover plate on the top of the motherboard cable bracket. After all the wires are organized in the correct order, I'll strip, crimp, and insert the pins into the 2 power supply connectors in place on the frame. With the connectors finished and plugged in, I'll cut 2 more lengths of reusable Velcro cable tie and wrap one around each of the 2 wire groups running up to the power supply. As we start to bring this video to an end, I thought it fitting to leave you with a few benchmarks of the improvements we've completed today. The points of interest I'll be highlighting are the aluminum housing of the 180-degree angle adapter, the 16-pin GPU power plug that is plugged into the angle adapter, the power wires that run along the back of the water block, the same wires as they bend to run along the motherboard, The point on the GPU water block's backplate that tends to transfer the highest heat load during heavy processing, and the point on the motherboard cable where the wires are most tightly wound together. One thing you'll notice on the thermal image itself is that I have not pinned a point of interest on the GPU power connector, as that will naturally become one of the hottest points registered in the image, so the red target will eventually hover over that point automatically as it warms up. Lastly, a final reference point is that these initial benchmarks were ran at a 2K resolution of 2560 by 1440, since that was the most easily accessible monitor at the time of running the benchmarks. The baseline temperature readings taken a few minutes after system boot are as follows. The angle adapter is steady around 26.8 degrees, the GPU power plug isn't yet hot enough to measure, but is roughly 27 degrees, both points along the GPU cable are oscillating between high 26 and low 27 degree values, the GPU backplate is registering mid 28 degrees, and the motherboard cable is oscillating between high 26 and low 27 degree values. Next, I performed 3 consecutive runs of Firestrike Extreme with measurements taken throughout, but I'm reporting on the peak values here. The peak reading of the angle adapter was 38.9 degrees, the GPU power plug reached 40.9 degrees, the GPU cable right behind the backplate was hitting 35 degrees, the GPU cable after the bend was oscillating between 30 and 31 degrees, the GPU backplate pegged at about 39.3 degrees, the motherboard cable reached 27.1 degrees, and during the Firestrike benchmarks, Hardware Monitor reported a maximum of 395.27 watts and a max temperature of 43 degrees on the overall GPU. After allowing the system to cool back down to near baseline, I ran about 10 minutes of Furmark. I rarely use this application, and when I do, it's to simply dump a healthy bit of power into a GPU, which is just what the doctor ordered here. The angle adapter has reached 51 degrees, the GPU power plug has been steadily oscillating between 55.3 and 56.5 degrees, and has been steady in that range for a few minutes. The GPU cable right behind the backplate is right around 45 degrees, the GPU cable after the bend is 37.5 degrees, the GPU backplate is 46.5 degrees, and the motherboard cable is oscillating between 29.6 and 30.3 degrees. Taking a look at Hardware Monitor after the Furmark run, we can see that at peak the GPU reached 450 watts and a max temperature of 48 degrees, with a hotspot reading of 55.6 degrees. I'm pleased overall with these readings, and even have a few more tricks that I may never demonstrate in an upcoming video that will further reduce the temperatures shown in these thermal readings. I've also captured some interesting benchmarks of similar tests being ran with GPU cables made with 18 and 16 gauge wire that I'd like to eventually share. But for today, this journey has gone as far as it can go. One thing I was hoping to include in this segment was the construction and mounting of the EPS cables, but I didn't quite get there. To save runtime on the next video, which is unlikely to ever see the light of day, I will construct those behind the scenes. At this time, all I have left to offer is a hope that you've enjoyed this demonstration, a thank you for watching, and to say, out.